This is a number that looks like Gauss when arranged like this, and in fact it was built to be a prime number that looks like Gauss, and we think with high probability that this is a prime number. What do I mean by high probability? We mean that they used what we call a probabilistic primality test to build this number, and we think with a very high confidence that this is a prime number. So let me show you what one of those probabilistic methods looks like. For this particular number, they used what's called the BPSW test, but for this video, I'm going to show you how to use the Miller-Rabin test. The Miller-Rabin test is built on two things. It's built on Fermat's little theorem and the fact that modulo p, the number 1, has exactly two square roots, plus and minus 1, and no other. Now, if p is an odd prime, p minus 1 is even. Write p minus 1 as 2 to the k times d, where d is odd. Now, if I have a base a that is relatively prime to p, then a to the 2 to the k times d will be congruent to 1 modulo p by Fermat's little theorem. Now, take that exponent and divide it by 2. Then this new number, a to the 2 to the k minus 1 times d, that number is a square root of 1, because if I square that number, I get the congruence above, and I will get 1 modulo p. So that number, because p is prime, has to be plus or minus 1. If I keep dividing that exponent by 2 as much as I can, then every one of those congruences has to be a 1 or a minus 1. So if I don't know if p is prime and I tried this out, and at some point in that sequence, I find that one of those numbers is not 1 or minus 1, then I have found a square root of 1 that is not plus or minus 1, and therefore p could not be prime. And if p is a number that I don't know if it's prime or not, but there is a base a where a to the p minus 1 is congruent to 1 modulo p, and as I divide p minus 1 by 2 by 4, or as much as I can divide by 2 and still get an integer, and I get all 1s or a minus 1, then we call that a strong probable prime in base a. And such a base a, we call it a witness for the primality of p. But if, on the other hand, p is in fact composite and a has this property, then we call a strong liar. As it turns out, liars are very rare, and in fact, for a given number n, only at most a fourth of all bases can be strong liars. Then if you don't know if n is prime or composite and you find a witness for its primality, then this is a liar with a probability at most a fourth. So this is 75% prime versus 25% composite. But if you choose two bases at random and it happens that they are both witnesses for the primality of n, then the probability that those are both at the same time liars, it's a fourth times a fourth. So now it's a 6.25% that this number is composite. If you use 5 bases at random and they are all witnesses for the primality of this number, then now the probability that this is composite is a fourth to the 5. So the probability is now something like 0.1%. And if you do this some 20 times and you all find witnesses for the primality, now the probability that this number is composite is something like 9 times 10 to the minus 11%. So super tiny. So let's do this test, the Miller-Rabin test for n, the number that looks like Gauss. This is the number. It turns out that n minus 1 is even, but not divisible by 4. So n minus 1 is 2 times d, where d is odd. So in this case, to run the test, you pick a base, so say a equals 2, and then raise it to the dth power. Now, 2 to the d has to be 1 or minus 1, and if it is 1 or minus 1, then this is a strong probable prime in base 2, which it is. In this case, 2 to the d is congruent to minus 1. If it was anything other than 1 or minus 1, then this would not be prime. It would be, in fact, composite, and we were done. Try again with a equals 3. 3 to the d is also congruent to minus 1. So this number is also a strong probable prime in base 3. Try a equals 5. It is also strong probable prime in base 5. Try the base 7. And in this case, 7 to the d is congruent to 1. So that means that, yes, it is still a strong probable prime in base 7. Let's pick some other base. Now the base is 1, 2, 3, 4, 5, 6, 7. It turns out that that number to the d is congruent to minus 1 modulo n. So it is also a strong probable prime in this base. So by now we have found 5 different bases that this is a strong probable prime in those bases. So now the probability that this is composite is down to 0.1%.